All right, are you ready? I'm just like trying to get so much done. I'm talking pretty quick. So maybe on the video you could slow me down. So on videos you could go in and like if I played this video here, we'll just go there and we'll hit play and I'll pause it. You could go here to speed and you could go to playback speed. You can say, whoa, dial that down, boy. And I don't really like that phrase boy because it kind of sounds like dog. And that brings back bad memories from my childhood. You can dial down the speed right there. So that's how you do that. And if I'm talking too fast, but I'm trying to get a lot done. So that's why. And I just get excited too. And I had a little caffeine this morning. Man, here we go. All right, bivariate. When I hear bivariate, I'm thinking bi to bicycle, biplane, bipartisan, right? Bi is really the prefix that means two, and vary is like variable. So we're talking about two variables here, and that's exactly what the definition says. Is we're talking about two variables. Why they put like te instead of like making this word variable? Why don't they just call it bivariable? But whatever. It's statistics. So we're talking about bivariate distribution, but when you see bivariate, just think bi, two, variables. It's two variables, okay? Just think that. So we're talking about a probability distribution involving two random variables, and that's called a bivariate probability distribution. Cool. Each outcome of a bivariate experiment consists of two values, one for each random variable. So each outcome of a bivariate experiment consists of two values, one for each random variable. And an example would be rolling a pair of dice. So you roll two dice, you're going to get two values for each outcome. You're going to get the value on one die, a value on the other die. So you'll have two values for each outcome by variable, bivariate. When dealing with bivariate probability distributions, we often are interested in the relationship between the random variables. And so we already saw this when we were looking at joint probabilities and restaurants. I'm going to go find that for you. Hold on. All right, so we already saw that when we were looking at restaurants. And so here is a cross tabulation, and the cross tabulation shows us two variables. And so this is just an example of two variables, and we had like the variable good and we had the variable meal price, and it gave us some data. So I kind of think of that when I think about two variables, and we're bringing together, is it good, very good, or excellent, this sort of nominal. I guess that would be nominal ordinal because there is a rank to that. This ordinal data along with, and then we have interval and we have ratio. This ratio data, because there's a 0 point, you can't have negatively priced meals. And so we have ordinal and ratio data, two pieces of data. I don't know if this relates, but that's what I think of. And so I'm just bringing that up for reference. So we can just pass that by. Just kind of what it makes me think of is what I'm going to put here. What bivariate makes me think of that we already saw, right? So we'll just put that there, and I'm going to not have that underlined. But here is an example of bivariate discrete probability distribution. And so, yeah, so check it out, cross tabulation, right? So this was called cross tabulation, and I need to move this down now. There we go. And so this one, and so we'll just highlight cross tabulation there. So we're like, oh yeah, we already kind of learned a little bit about cross tabulation. So that's kind of good. I didn't even realize that was going to be there. And so here's cross tabulation again, and we'll just bright yellow that to kind of match the previous slide. So we saw that cross tabulation. Here's another cross tabulation. Bivariate discrete probability distribution. We have two dealerships. We have the Saratoga dealership, and we also have the Geneva dealership. And here's how many cars the Geneva dealership sold per day. And then that's 0, 1, 2, 3. And here's how many cars the Saratoga dealership sold per day. 0, 1, 2, 3, 4, 5. And so Saratoga dealership will sell 4 or 5 cars per day, but apparently Geneva never sells 4 or 5 per day. And out of 300 days, how many days were there like 0 sales at Geneva and 0 sales at Saratoga? There are 21 days. How many days were there 1 sale at Saratoga and 0 at Geneva? There were 30 days where there's 1 sale out of 300, 30 days out of 300. There was 1 day where Saratoga sold 30 cars and Geneva sold 0. Sorry, there was 30 days where Saratoga sold 1 car and Geneva sold 0. So here you have this cross tabulation that shows you here how many days did certain things occur. So if I said here, we had 12 days out of 300 where Saratoga sold 3 cars and Geneva sold 2 cars, right? So that's how that works, right? Bivariate, and bivariate again is by to variate variable. It's 2 variables, and it's the distribution of what occurred. And so here's a probability distribution. So we can make this more look like probability by taking each of these here and dividing it by 300, and it'll show us like what percent of the time. And remember, probability has to add up to 1, or if it's percentage, to 100%. There is no 150%. There's no 110%. By definition, 100% is 100%. Even though colloquially, as we'll speak just kind of like in common idioms that humans use, we'll say, give it 110%. No, mathematically, the definition of 100% is the totality. It's the whole. There's nothing more than that. So this is when we figure out the probability of each one of these occurring by dividing each one by 300. That will give us a decimal, and that's the probability. All the probabilities have to add up to 1, or if we make them percentages by multiplying each probability by 100, all the percentages need to add up to 100%, because 100% is 100%, and that's the totality, that's the whole. There's nothing more than that in mathematics and statistics. All right, and then we have our marginal probabilities out here on the side, where we'd have those are marginal probabilities, and these are marginal probabilities, showing us what's the probability of having a day where Geneva sells none. It'd be 86 over 300. So when we do all that division, 86 over 300, I'm going to bring up my calculator, and calculator. That's kind of like talk to you later, calculator, and divide that by 300. 86 divided by 300, we get 2867, 2867. And so that's how all these numbers are calculated there, is each number there in each spot divided by 300. So we did 21 divided by 300. So I'm just going to clear all that out and do 21 divided by 300, and we get 0.07. And at this point right here is 0.07, right? 0.07. And if we multiply all those by 100, we get percentages. So this is our bivariate discrete probability distribution. Discrete, remember, is like whole numbers. We can't sell fractions of a car. So discrete means we're selling 0, 1, 2, 3, 4, 5 cars. And continuous would be like height or distance or time, where you could have fractional measures. All right, so that's discrete probability distribution. There it is. And then we could calculate the expected value and variance for daily car sales. And notice this is just at Geneva. So we were looking at both Geneva and Saratoga, but now we're stepping down just to look at Geneva. And Geneva has the 0, 1, 2, or 3. And here we're seeing the 0, 1, 2, or 3 of how many cars were sold. And then we have the probability of selling 0 cars, 2.867. So 0 is 2.867, the probability of that happening. 1 is 0.37. 1 is 0.37. So we have those probabilities. And then when we multiply that random variable by the probability, we get these values. And when we add them up, we get the expected value, or the mean, which is that. And when we take this value, the random variable, and minus the mean, right? So 0 minus 1.1435 is negative 1.1435. 1 minus 1.1435 is negative 0.1435. So we are now calculating the variance. So we take each data point, each random variable, and we subtract the mean, and that's what we get here. And then we square it. So when we square these values, we get these values. And then we multiply it by the probability. So 1.3076 times 0 is 0.3749. That's not right. That's not right. 0 times anything is 0. And 1 times 0.02, I need the probability here. Sorry. We multiply it by the fx. So we put this in here. We get this probability here. Put the 0, the random variable, into the function. We get the probability. So the probability fx, 2.2867 times 1.3076 is that. And 0.37 times that is that, and so on and so forth. And then we add all those up, and we get this right here, and that's our variance. And if we took the square root of that, we would have our standard deviation. This is the data for the expected value, the variance, and we could square root that to get the standard deviation for the Geneva dealership. So here are all those tables that we just saw, 1, 2, and 3 right here. And then here we have both of them. And so when we do, and so that was for, I'm sorry, that was for Geneva, not Saratoga. So I need need to do Geneva here. 3749, 3749, 076, 076, 8696. Yep, so that's Geneva. So I'm going to put Geneva here. Geneva here. And now we could calculate it for both of them. So here's both of them. And I'm just going to make that like this is both, right? And so for both of them, you have to kind of pause and kind of take this in here. So we have 0, 1, 2, 3, 4, 5, 6, 7, or 8 is our S. And our S is a random variable. And we have 0 is 0.7 at the time. So we have, notice we have, let's see, all right. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Let's see if we can make sense of this. So 0, right, when we sold 0 cars at Saratoga and 0 cars at Geneva is 0.7. When we sold one car, what's the probability of one car being sold at both Saratoga and Geneva together? Well, here we have 0 and 1, right? So 1 was sold at Geneva and none were sold at Saratoga. But we also have this, where 1 was sold at Saratoga, but none were sold at Geneva. When we add 0.07 to 0.1, we get 0.17, right? Well, what about when 2 cars were sold? Where were 2 cars sold? Well, here's where 2 cars were sold. 1 was sold at each location. 1 was sold at Saratoga, and 1 was sold at Geneva. That's 2 cars. Or we could have 0 were sold at Saratoga, and 2 were sold at Geneva. That's 2 cars. Or we could have 2 were sold at Saratoga and 0 were sold at Geneva. So we're looking at this angle right here, and we add 0.08 to 0.12 to 0.3. This gives us 0.2, and that 0.2 plus 0.03 gives us 0.23, 0.23 right here. And then for 3 cars, here's 3 and 0, and then here's 2 and 1, and then here's 1 and 2, and then here's 0 and 3. So all of these numbers added up. 1.11 plus that is 0.14. And 0.14 plus 1.4 is 0.28, and 0.28 plus that's 0.29. And so for 3 cars, we have 0.29. You do all that for each of these random variables for both dealerships. We have that random variable. We have this probability, and then if we want to calculate here the variable times the probability, we get these values, and we add those up. We get our expected value or our mean. And then we subtract each data point, each random variable from the mean. So 0 minus that is this. 1 minus the expected value mean is that. We get that. We square it. We get this. And then we multiply this by the probability of that occurring. And we get that. And then we add all those up and we get the variance. And if we took the square root of that, we get the standard deviation. So that, my friends, ladies and gentlemen, is bivariate distribution. And bivariate is 2 variables, bi, 2, and variable, 2 variables. And this is a bivariate 2 variable probability distribution. And it's a whole heck of a lot like, well, it is. It's cross tabulation, right? There, the textbook is using cross tabulation to describe it. And previously we saw cross tabulation to look at restaurants right there. So that is that's bivariate probability distributions and calculating the expected value and calculating the variance. And if we want to, we could square root the variance and get the standard deviation for those bivariate probability distributions. And the next one, we're going to see how to do covariance and also correlation for bivariate probability distributions. And that covariance and correlation measure the relationship between the values. Between, like, you know, the data points for Geneva and Saratoga. Is there a relationship between all these data points? And we'll use covariance. How much do they vary in combination with each other? Like, and then also correlation, right? How much are they related to each other? How much do they correlate with each other? See that in the next video.